All right, next we have Felipe Gomez from Harvard University. He's in the fields of information theory and machine learning, and his advisor is Flavio Calmon, and he did two practicums, both at Princeton Plasma Physics Laboratory. Let's welcome Felipe.
Thank you. All right, everyone hear me okay? Awesome. Get excited, guys. This is the last presentation of the day. All right, so today we're going to be talking about differentially private algorithms. Now, I'm going to assume that this audience doesn't think about privacy in a mathematically rigorous way on a daily basis. I do. So for the first part of this talk, I'm going to try to elaborate a little more on what exactly I mean by this phrase in particular, private algorithms. And so I'll just isolate that for now and just take a pause. I do want to take like 5 seconds here and just pose these questions of what is a private algorithm and what properties should it have. And I want to pause here because I'm part of a community of statisticians and theoretical computer scientists that have more or less agreed on a definition of what this means. And I'm going to give that definition to y'all. But afterwards, please tell me if this actually aligns with what you expect a quote-unquote private algorithm to be like. I am very curious. And so we begin with a toy model, right, as most of us do. And we act like there is a curator. They have some data set D. Here for the curator, I have a hospital. That's always my working toy model that I work with, although this can be anything. And they're going to release some statistics. They don't want to release their data set into clear because it's a very sensitive data set. However, the data set has a lot of very interesting properties that they want to share with people. And so they're going to run it through A. A here is an algorithm. And they're going to release the output of this algorithm. I'm going to call this quantity theta. It's just at least how I denote it. And they're going to send this over to some interested third party. This third party can be literally anyone. They could open source their statistics and release it to the whole world, or this could be some intermediary. And the intended use of theta, the intended use of what they're sending is for data analysis, is to have some general property about the data set, but the intended purpose is not to leak information and to not release any particular sensitive elements of this data. The problem is that's not the real world. Every single time you release statistics, there might be someone malicious who sees these statistics. And I'm going to denote that here by this very scary looking adversary. And the goal of the adversary is not to do data analysis. Their goal is not to learn something general about the data set and extrapolate it to some distribution. Their goal is to reconstruct the data set for some malicious purpose. And this is the toy model that we typically work with. This toy model is quite general, and there's a lot of applications of it. I guess the most interesting application, or I imagine the one that's closest to home for this audience, is that they're scientists and they want to publish some statistical results about some data sets. And maybe your data set, for whatever reason, you don't want to release it. But you do publish some average quantities about it. Can those average quantities be used to reconstruct the data set? I don't know. A company and university might train an AI model and they might open source it. Weird way to think about it, but an AI model is, it's trained on the data. It might leak sensitive information about the data set. So this is another variation of the same problem. The governments, and in particular here I'm thinking of the census, they might release data sets about their population. Can you use census statistics to reconstruct or learn something about the US population? And the last one, which is of particular recently it's become of interest to the community is a third parties purchasing data, user data from tech companies. Depending on the type of purchase, they can either purchase your data directly or they can purchase some aggregate statistics about it. And so once again, the same problem holds here too. Okay, so we have this toy model. How do we rigorously define a privacy breach? What does that mean in this case? And communities spend a really long time thinking about this problem. And the consensus, finally, after like 15 years of thinking about it, is that it's a really hard thing to answer. And the problem is it's really hard to put into a mathematical framework. And the reason why is because when you try to do it, you will either you will call things privacy breaches that no reasonable person would define as a privacy breach. Or the opposite will happen, where some attacks that are very clearly privacy breaches, according to the mathematical model, it's just not a privacy breach. It's very hard to find that like good in between balancing these two effects. And so what the community has done is something I call the sandwich technique. I got this from someone else, Kobe Nassim, who's a theoretical computer scientist. He's wonderful. But he calls it the sandwich technique. And the basic idea is that you can't really define what a privacy breach is, but you can write down the conditions that are sufficient to prevent a privacy breach. And note here that I say just sufficient, not necessary and sufficient. So you can give an idea of a very, very private algorithm that any reasonable person will call private. That's easy to do. And you can do the opposite. You can write down which conditions indicate that a very obvious breach is coming. You can do that too. And the most interesting thing, or like the key insight here, is that both of these extremes are easier to give a mathematical framework. And because you have these two approaches, you can kind of sandwich this like vague idea of a privacy breach between these two bounds. And that's how, at least this community has decided to think about privacy breaches. And in particular for today, we're going to be focusing on this side of the inequality. So we're going to think about conditions that are definitely sufficient to prevent a privacy attack. And this niche is exactly how we get to this notion called differential privacy. For those of y'all that haven't heard of it, the idea is to provide some sufficient conditions of which you can guarantee that your data is going to be protected. Like I've been trying to motivate, DP is how I'm going to refer to differential privacy. It's a very strong notion of privacy. I'm going to give you all the definition, and your reaction should be, oh my God, really? Like, it's meant to be very, very strong, and that is intentional. But the goal is to give a rigorous definition of privacy that's based on worst case scenarios. At every single step of the analysis, you think, what is the worst possible thing that can happen from the point of view of privacy? And we assume that is going to happen, and we try to protect against that. And that looks really, really weird. At least it did to me at the beginning. And the reason why that we think about things this way is that the more you assume that the worst case is going to happen, that translates into more assumptions that actually simplify the math. So just keep that in mind. With that primer, I can finally start trying to get to the definition of differential privacy. Again, this is our threat model here. We're sending some statistic directly to an adversary. Their goal is to reconstruct the data. And so I always like to describe things in terms of this thing that I call a threat model, which is just this, like, I guess it's like an algorithmic way of thinking about this. Step one, we have a data curator, and they generate some statistics data. This is what I've been showing pictorially up until now. The adversary is going to receive it, but also, like, what are their capabilities? What can they do? What do we assume they can do? We need to answer this before we can continue thinking about the problem. And because this is differential privacy, we're going to assume the worst case scenario. What's the worst case scenario? The adversary has all internal details about the algorithm A. So if you're computing an average over the data set, they know you're computing the average, and they have your code for how to do it. Worst case scenario number one, so maybe they're an internal in the company, maybe they're a collaborator of yours. They're not some unknown person. They know quite a lot about what you're doing. Worst case scenario number two, this is even crazier in my opinion. They have actually successfully reconstructed the entire data set already, except for one element. They're missing the final piece of the puzzle. They're not quite sure what it is. And the last thing they know is your information, which I will denote by Z. Here, this can be arbitrary. In the community, we often call it Alice, but I like calling it your information in particular. So what I'm trying to get at here is that the adversary has figured almost this entire problem out. Except for one thing. They don't know this statistic was generated by this data set, D prime, that they already have. This is supposed to be D prime, by the way. Sorry about that, Microsoft. Anyway, they don't know if the statistic was generated by this data set, D prime, that they already have, or D prime plus your data. So the only thing they haven't figured out is whether you participated or not. They only need to guess one bit of information. Are you in this data set or not, given this input theta? So again, hopefully the reaction is, oh my gosh, really? Yes, this is meant to be sufficient for privacy. Yeah, so the goal of the adversary is to infer that you are in the data set D. And that is the threat model for differential privacy. A question to you, how would you even defend against this? This is a very powerful model. For one thing, the adversary, they can just run the algorithm on the data set that they've already reconstructed, because we assume they have most of the data set. We assume they have the algorithm. They can just run it. And they can also run it with your data included. They can do both those things, and they can compare against the statistic data. They're free to do that. And so any deterministic algorithm is going to stand no chance in this threat model, right? Because then they can just run both cases and then get back and immediately determine if you are in the data set or not. Also, kind of by assumption here, the adversary also has all private keys for any encryption that you do. So even any cryptographic procedure here is going to stand no chance. There is no notion of private or public keys or any of that stuff that's typically assumed in the cryptographic literature. And so even cryptography here is not really going to help you. And so my claim, I'm sure there are other ways to protect against this, but one way to protect against this is via randomness. So instead of having a deterministic algorithm that runs some sort of statistical approach, you do it in some sort of randomized way. And so let's go back to this idea, like this intuition that I showed earlier. The adversary can just run on the data set they have and the data set with your data and make some inference about which one you did. And let's assume the algorithm is very simple. We call this a sum query, where your data set, you're just gonna sum over all the elements in the data set. Let's say the data set is full of like integers, and you can just sum them. But instead of just releasing the sum, you release the sum and you add a little bit of Gaussian noise. That's what this calligraphic N here is meant to be Gaussian noise with some variance, sigma squared. And let's call this like this sum over the data set. Let's just call that d bar, just so I can simplify the notation a little. And so what that means is that when the adversary runs on the data set they've already reconstructed, they're going to get a random variable now. They're going to get a number out, but that number is going to be Gaussian. It's going to be random. But when they run on your data, with your data, it's going to be a Gaussian centered at a different value, at the total of the data set plus the contribution of your data. So now these are two random variables, and the adversary needs to determine which one they're working with. You know, they only have theta, which is a number. Theta came from one of these two distributions. Which one did it come from, right? And so now the adversary needs to do some sort of statistical test. It's no longer guaranteed that they can actually figure this out. And we've made it a little harder on the adversary by introducing some randomness. And that's the key idea of deferential privacy, is that all your privacy is actually, like the randomness is the source of your privacy. It's not anything else. And so with all that primer out of the way, finally get to the definition of deferential privacy, which is, I'm going to give a vague version of it. Thank you. Which is that if you're deferentially private only if it is difficult to statistically distinguish between these two distributions, where D prime and D double prime are any two data sets that, I forgot to mention this here, that differ by one element. If two data sets that differ by one element, so that element is, you should think of as your data. And if it's difficult to statistically distinguish between these two distributions, right? Because we're using randomness for privacy, so these are distributions, then we say we're deferentially private. But how do we define difficult to statistically distinguish? There's a lot of possible definitions you can give. And in fact, the community would agree with you, because we haven't come up with a good way yet. Here are all the variations that I'm aware of for how to define difficult to statistically distinguish, and each one of them is going to give you a slightly different definition of deferential privacy. I lied to you earlier. I said these are all the different ways. I lied. There's actually more variations. Here's another slide. Where's my favorite definition? Oh, it's not here because I actually have another slide. There you go. This one is my favorite. Fun fact, F deferential privacy came out in 2021. It's a bit of a joke that there's just so many to choose from. I have one more slide showing all the different variations. We're finally at the end of table 3 of one of my favorite papers in the community. It's called Deferential Privacies. But all this to say that it's actually, like, there is no one way to talk about deferential privacy. There are so many variations. It's actually quite overwhelming when you first come into the literature. And so instead of talking about a definition of deferential privacy, I'm going to talk about my favorite definition of deferential privacy. I need to hurry up here because I've taken a little bit too much time here, as I love talking about this. But like, my criteria for choosing my favorite variation of deferential privacy is that someone outside of the statistics community should be able to understand what we mean when we say these two distributions are difficult to statistically distinguish. And so I came up with this, well, no, this is, to be clear, this is not my definition by any means, but this is why it's one of my favorites. We say it's differentially private if the adversary cannot distinguish between these two distributions with accuracy higher than some number, I call it eta here. So that means that like no matter what attack the adversary makes to determine if you're in the data set or not, their accuracy in doing that is bounded. And it's bounded by this number that I will call eta. And so with all that primer out of the way, now that we have a definition for privacy, And so again, one thing I want to emphasize here, the intuition is that if this adversary in this very strong framework cannot determine your data cannot determine or like identify you with some accuracy, then neither can any realistic adversary you will actually encounter in the real world, right? By protecting against this extremely powerful threat model, you get protection in the real world too. And so this is my first contribution. I don't have time to like really, I also did not even try to explain what this blue curve is. But this blue curve is what, let's say the community, is how the community would compute this earlier, like before my contributions. And the point is that, one of my contributions is that you have this framework for how to compute this noise. And you can get about 4 times less noise for the same accuracy when you do it this way. I am out of time because I blabbered too long, and that's okay. The main thing I will say here is that here power replaced this with accuracy. I did not have time to explain what it is. But the point is that so far I've just been talking about like any general algorithm. I came up with a framework of how to do this for neural networks too. So you can make neural networks differentially private and bound them in this particular way. Here's like a quick simulation of like the noise that you need to add. Here we add Gaussian noise to the gradients. That's how you make neural networks differentially private. And my framework allows for about a factor of 2 less noise that you need to add in order to get the same privacy guarantees. And so this, here we made some language models experiments. Here's GPT-2 fine-tuned on some data sets, and you see a uniform improvement with our approach. And that's fun. And then remarks, don't have time for that. Anyway, my final conclusions is that I think deferential privacy will play a key role in our society in the future. There's still lots to do. With my research that I've done in my PhD, I've seen about a 10% improvement in the accuracy of our neural networks, our private neural networks. But there's still a long way to go. We're still very much we're less accurate than the non-private counterparts. And I think we can get there. And I'm also very interested in thinking about like not worst case guarantees and making the adversary a little bit less powerful. And with that, I'd like to thank the CSGF for funding me for this type of research. Thank you, guys.